Welcome everyone to our webinar on system stability in a renewables-based power system. My name is Emeline Spier. I'm Director Europe at Agora Energiewende, and I'm absolutely delighted to welcome you all today. A few words on Agora. We are an independent think tank. What we do is we develop science-based and politically feasible strategies for climate neutrality. And to do that, we focus on data and evidence building and also very much on stakeholder dialogue. We do this from Berlin, from Brussels, and increasingly on an international scale. We have an office in Beijing, a partner organization in China, and also a network of partner think tanks across the world, which is called INET. Now, on the way to climate neutrality, the power system is the first mover and is moving quite fast. Pretty much all scenarios that we have show that to achieve net zero across the European economy by 2050, the power system must be decarbonized or nearly decarbonized by 2040. And as we well know, this will require a shift, or largely a shift, from large centralized power plants with rotating masses to smaller decentralized power plants and storage systems connected by inverters. And this has been happening rather fast. In the first half of this year, already 50% of the power production in the EU is renewable, 30% comes from wind and solar. And in 2030, we are meant to reach more or less 70% of renewables in the European power mix already. I'm here talking, of course, about average energy production figures, but system operators would know that what matters as well is the instantaneous share of inverter-based generation in the system, which, for example, in Germany, we have seen can be occasionally as high as 77%. And this is where system stability comes in. While the operating philosophy that we've had has been historically built around the mechanical capabilities of the conventional power plants, how do we need to evolve this in the new system? It is an issue that is both quite technical, not always as high on the agenda as it may need to be, we have found, but on which decisions and key choices need to be taken in the short term and are actually being taken in the short term in a variety of countries and also at European level. And here I'm referring to the Network Code on Requirements for Generators, which is currently being revised by the European Commission. So when we started working on this a year ago, we decided to start by helping to make this complex topic more accessible to a wide range of stakeholders by describing, explaining system stability needs, the different contributing technologies, and the deployment strategies. We will publish the result of this work tomorrow or in the very next days of next week. What we have also done is we have initiated a broad stakeholder dialogue and realized that for this issue in particular, we realized how crucial it was to bring the relevant people together, system operators, producers, manufacturers, authorities, and regulators. Our ambition here is really to support informed decision-making so that system stability is addressed both early enough not to slow up the scale-up of RES, but also cost efficiency, as we all know it's very important to keep in mind the affordability of electricity. For this work, we have commissioned Moeller Poeller Engineering, and you will hear in a few minutes Mr. Marcus Poeller, whom I would like to thank for a very rich and insightful report, and also for our many discussions in which we have learned quite a lot. I would also like to thank all our distinguished panelists. We are eager to share and debate the findings that we've had with you today. I'm now going to hand over to my colleague Alexander Dussold, who has led this work internally for which I would like to thank him warmly. Alex, over to you.
Thanks a lot, Emmeline, and welcome to everybody listening in. Thanks a lot for joining. I'm very happy today, especially when I look out of the window. Brussels roofs are white, so probably good that we have this as a webinar and not as a physical meeting. And today we talk about system stability, a topic that I actually tried to address already in 2016, but somehow found deaf ears on the topic and get answers like, it's not yet the time for it. Let's wait 10 years to discuss that. And now we are nearly 10 years later, and we see the energy transition is really moving forward. We're in the middle of it. And finally, we get to talk about system stability. And many stakeholders have already understood how important it is for a stable electricity system. The transition and also low costs for the electricity we pay. So in today's webinar, we'll hear first from Markus. He's presenting us his report on the different topics of identifying system needs, technologies that can provide them, and on which strategies can fulfill these needs and lead to the investments. Feel free to drop your questions while he presents in the Q&A field. Also, we will have some more Menti questions to keep you engaged, and questions will come in one by one through the webinar chat. One question stays open about 5 minutes, and we'll inform you when the next question is online. So keep a look on the webinar chat to see when the next question is opened. We'll look at the answers later on after the panel discussion. And so, yeah, Markus will start. I will then present key findings that we derive from the project. We'll go on to the panel discussion with speakers from system operators and gas turbines, wind turbines, and battery industry. Mr. Poeller is also on the panel. And then have time for Q&A. So please drop your questions in the Q&A. My colleagues, Karen, is sitting in the back and looking at them and suggesting then questions to be addressed to the panelists. Yeah, and now I'm very much looking forward to hear Markus Poeller and his presentation.
Yeah, good morning from my side. When I look out of the window, everything is gray, so I think white is better, Alex. Good. I'm now going to present a summary of the report that we have prepared for Agora Energiewende, a report about system stability, and in particular about the impact of variable renewables on system stability. So let me share my slides. Okay, so I hope it's all right now. Good, so the title of the report is System Stability in a Renewables-based Power System. Renewables-based means that we have a large share of renewables, essentially variable renewables, which is wind and solar. And the report covers first in an introduction general terms and definitions of power system stability. Then we are looking at the impact of variable renewables on power system stability, which has, of course, a lot to do with inverter-based generation, but also with the fact that our load flows in the system are changing because variable renewables are typically not installed close to the load centers, but further away and at lower voltage levels. And then the next sections are about how to deal with the new challenges. First of all, an overview and introduction to the concept of system services, and also to the technologies that can provide these services which are required to support system stability, and strategies, especially procurement strategies of system operators to ensure that these services will be available and that system security will be maintained. And then also processes and tools which help system operators to support them in their daily work to maintain system stability and system security. Now, this presentation here is essentially about the two main aspects about the fundamentals, and I think all the rest will then more be covered in our panel discussion. What you see here are the general stability definitions. We are here referring to the definitions of the IEEE SIGRE working group back in 2004, which was still led by Prada Kundur. Since then, there were some other working groups updating these definitions, but it more or less ended up in introducing more and more categories and different types of stability. I prefer actually retaining with these definitions because I think that all other stability aspects can actually refer back to these categories which were defined back in 2004. As a general concept, system stability of any kind of physical system is defined as the capability of a system to return back to a steady state after the system has been subject to a disturbance. So this is also defined like that in the IEEE SIGRE paper of 2004, and of course refers back to general control theory, systems theory, and so forth. Now, when we analyze stability in power systems, then we can further distinguish some different types of instability. First of all, and this I would say is the best known stability aspect, it's about the generation demand balance. Everybody probably knows that a power system has to maintain a balance between generation and load at any moment in time. And if there's a deficit in the active, either deficit in generation or an excess in generation, this is then made visible by the frequency. So the frequency indicates whether we see an active power excess or an active power deficit in the system. Then there are some stability phenomena which are referring to the stable transmission of power. So when we say transmission, there must always be a line or a transformer or something that we transfer the power across involved. And this is then rotor angle stability, which we could also name synchronous machine stability because it directly refers to the rotor angles of synchronous machines, which must remain in synchronism. And we have voltage stability. Voltage stability can actually be a problem also to any kind of generation. It is not necessarily linked to synchronous machines. And then there's a fourth category of stability aspects, which is very often named resonance stability. These are all other types of instability that do not happen at fundamental frequency, but in higher frequency ranges or frequency ranges below fundamental frequency. Now let's have a closer look at these stability phenomena. First of all, frequency stability. What we find here is the frequency response of a system in case of a large generator outage. You see, first of all, the frequency goes down, and the first important parameter is the initial rate of change of frequency here. So how steeply does the frequency go down? Then there is the so-called frequency nadir. This is the lowest point of the frequency. And then afterwards, the governors, the speed governors that drive the turbines back, drive the turbines up, and the frequency is driven back into its nominal frequency range, which in the European systems is defined by plus minus 200 millihertz around nominal frequency. And then in the longer run, the frequency would be driven back closer to the 50 hertz or to its nominal value by the primary frequency controller. That's the primary frequency control already. So by the secondary frequency control, and then in the longer run, also by the so-called minute reserve. So the parameters which are having an impact on this is the inertia. Sorry, it's my mobile phone. I cannot turn off the steady phone, but the mobile phone I can turn off, yeah. So it's mainly impacted by system inertia and also by the active power deficit or the active power excess. In the continental European system, the reference incident is a generator outage of 3000 megawatt. But frequency stability is not only of concern if a generator trips, but also if basically the interconnected system is splitting into different areas. In this example here, you can see two areas, an area A1 and an area A2, and an active power transfer between the two areas. And all of a sudden, the interconnector gets split. And you can see on the left-hand side, the system having a power export prior to the system split will experience a frequency excess, a frequency rise. And the area that is importing power prior to the split will see a frequency drop. So these system split events are much more severe than generator outages because the power transfers can be much higher than a generator outage. And therefore, classically, it's also accepted that in the importing area, such an event is actually managed not only by the primary control of the system, but also with the help of load shedding. But what can actually initiate such a system event, such a system split? A system split can be initiated if the stable power transmission is actually becoming unstable. So if we have no stable power transmission, so if the stability of the power transmission is lost. And here we have the different stability aspects that we need to distinguish. So actually, what can happen with the power transmission? What you see here in the upper right corner is a reactance. That could be a line or a set of lines. And now we are studying how the active power transfer depends on the voltage angle and on the voltage magnitude at the two sides. And many of you probably know this very well. This can be expressed by such a sinusoidal characteristic where the P max, so the maximum power on this curve, is defined by the voltages at the two sides. So V1 times V2 divided by the equivalent reactance. So it means that the higher the voltages, the higher is the P max, and the lower the equivalent reactance, the higher is P max. And if all of a sudden the voltages here drop, also the P max drops and the red curves would move closer to the orange curve. And the same thing can happen if, for instance, because some lines are tripping, the X is all of a sudden increasing, then also the P max drops. And now what you can see here at a value of 3000 megawatt, there's an intended power transfer across this transmission corridor. And now if we find ourselves on the red curve, then there's an intersection between the green curve and the red curve, and this is our operating point. Now, if we do not have enough voltage support, it can happen that the red curve goes down towards the orange curve, and then all of a sudden we don't find that intersection anymore. And if there's actually no intersection, it simply means that the system or the line corridor in this case would not be able to transfer the required power. And then the system becomes unstable right away. And this is what we typically name a voltage instability. Now, if we have an operating point, it can be stable. Unfortunately, it is usually stable. But there can still be some instability aspects, or it can still happen that the system is unstable, even if there's such an operating point. And this is the rotor angle stability that we find here. There's first of all the small disturbance rotor angle stability, which is also named oscillatory stability. And what I'm showing here in this diagram is an event that has happened in December 2016, where also the sudden trip of a line has initiated an oscillatory instability. You see here in green, that's the frequency in Spain. And here in the middle, we see the frequency more in the center of Europe, Germany and France. And what you can see here is an inter-area oscillation with a frequency of 0.115 Hertz. So a very low frequency inter-area oscillation. Also Turkey, all in the east, has had an impact. So this is the so-called east-west mode of the continental European system, which is well known and well studied. In this case, the event did not lead to a system split because the system operators managed to deload the transmission corridor, which then created positive damping, and then it decayed. Back in 2006, a similar oscillatory instability finally led to a system split. If the undamping is actually too fast, then there's no time to react, and then the system would lose synchronism, and the system would be split into 2 or more areas. Back in 2006, there were even 3 areas. The other rotor angle stability problem that is studied is the transient stability. That's directly linked to a set of synchronous machines or even a single synchronous generator. And in contrast to oscillatory stability, transient stability is always about a large disturbance, about faults, about short circuits. It is not just a system property, but it also has to do with the type of disturbance. So in blue, you see the frequency or the speed of a generator. If the fault was cleared sufficiently quickly, so faster within shorter time than the critical fault clearing time. And in the red case, the fault clearing time was above the critical fault clearing time, and below you can see speed or frequency. And you see the synchronous generators are not able to back synchronize and immediately lose synchronism, typically within 1, 2, or 3 seconds. And then a single generator or a set of generator becomes unstable. So this is rotor angle stability, and this is directly linked to the electromechanical interactions of synchronous machines. But we also said that a system could become unstable if there's no operating point at all. Why do we name this voltage instability? We name it voltage instability because it's usually initiated by a low voltage. You can see here, if you have a low voltage, the P max drops. And what you can also see here in blue is now not only the active power, which is in orange, but also the reactive power across our X. And what you can see here is that the higher the power transfer, so the larger the voltage angle, the higher is the reactive power demand of this reactance. And then if the sources which are here located at the 2 sides of that line are not able to cover the increased reactive power need, the voltage goes down, drives the orange curve downwards, and then basically the stability is lost. An example for such a voltage collapse, a short-term voltage collapse, is this one here. That's the System Black event in South Australia in 2016, also 2016. Here, there were very adverse weather conditions in South Australia. So that's the area around Adelaide. There were many short circuits on lines. There were some transmission lines that even collapsed. And as a consequence, there were several short circuits within a very short period of time. And because of this multitude of voltage dips, several wind farms tripped in South Australia, and losing generation means that the power import into South Australia was increased. And it was so much increased that it exceeded the voltage constraint stability limit of this interconnector. And as a consequence, the voltage collapsed. You see, we have this voltage collapse initially on both sides of the link. And then synchronism got lost. So the system was split apart. The South Australian system was split apart from the rest of the NEM system. And you see here in green, the voltage tries to recover, but then the system collapsed because there was practically no inertia left in South Australia. Whereas, and this is the red curve, in the rest of the Australian system, the NEM system, voltage was maintained. So this is an example for a voltage collapse.
Markus, if I may quickly come in,
Yeah, I know.
if the second part could be a bit quicker, like we
Yeah.
have 10 minutes for the part. Thank you.
I will hurry up. Finally, which we shouldn't forget, especially in the context of inverters, is the resonance instability. It's not new, but I would say it's more important nowadays because the converters that we have in the system, they have very fast controllers. And if we have fast controllers, so controllers with a large bandwidth, there can also be instability in higher frequency ranges. And this is what is typically named resonance instability. In case of a resonance instability, there's typically an interaction between a fast controller and the electrical network. And this can then lead to an instability at high frequencies like 500 Hertz, 800 Hertz, or even higher, or also in the subsynchronous range, so at frequencies which are far below the 50 Hertz. And this is I wouldn't say a new aspect, but it's new that it really has gained relevance. So we also had HVDC related controller instability, or also subsynchronous resonance is in general also part of this stability category. Now, in which way do variable renewables have an impact on power system stability? What you see here is a schematic view of a conventional power system. In this conventional power system, we have large power plants connected to the main transmission levels. And additionally, our power plants have typically been also fairly close to the load centers. Now, in a system with large share of variable renewables, we find many more generators on lower voltage levels, sub-transmission levels like 132 kV or 110 kV, and in remote areas, as we see it here. And they basically replace, first of all, temporarily during times of high wind and PV generation, and at a later stage, maybe also permanently, the large synchronous generators. So basically, there are two aspects which we have to analyze. One aspect is the different type and the different characteristics of the generators, so inverter-based generation in contrast to synchronous machine-based generation, and then also the impact that the more remote location of the generation has, which then results in larger power flows towards the load centers. So we can first of all say here, the system change is first of all that we have converter-based generation, which is very often also named non-synchronous generation. And non-synchronous generation leads to reduced short circuits, reduced inertia, and reduced synchronizing power. Here we assume that the non-synchronous generation is inverter-based generation with grid following generation. With grid forming inverters, we would then have synchronous generation in this sense. And then the remote location and the allocation of the generation at lower voltage levels means that we have a reduced voltage support. reduced short-circuit currents as well, especially in the load centers. Also reduced synchronizing power because the equivalent reactances are getting bigger, and very important, increased inter-area power flows. So all these blue arrows, they would also apply if our wind and PV farms were driven by synchronous machines. So it's not all about inverter-based generation if we discussed the stability impact of Weber renewables. A part of it is, but not everything. You know? So we can summarize it in a way that basically we have a negative impact of VRE, and it's mainly a result that they are passive, so they do not actively contribute. But if we do stability studies, we can also see that there's a positive impact of VRE on some stability aspects, because they are passive. Yeah? For instance, there's no rotor angle instability in case of a converter-based generator. It simply doesn't have a rotor angle. Of course, there are other instabilities that can happen, but certainly no rotor angle instability. So it's passive, so it means it doesn't contribute, but it also has less stability problems itself. So we can say stability in general is becoming different. It's not necessarily becoming worse compared to a synchronous machine-based power system, but it's different. And this needs to be studied. And of course, we have to change things so that we can maintain stability also in the future power system. Stability in system services, so that what is needed to ensure that the system remains stable? The term or the concept of system services is that we define technical properties, technical characteristics independent from technologies, components that are able to provide these services. That's basically technology neutral. So we have active power services like the typical primary, secondary, tertiary reserve. Then for the demand, frequency-sensitive demand response can contribute, artificial inertia, fast frequent control, and synchronizing inertia. Synchronizing inertia is basically something that behaves like a voltage source. So it's basically synchronizing the system. It helps synchronizing the system, and it also provides inertia, which is also always needed to synchronize the system as well. And then there are reactive power-based services like static voltage support, dynamic voltage support, and short-circuit currents. And here we have also listed black start capability. This is needed if stability has lost and system has collapsed and needs to be restored. Now you see these active power-based services, they mainly impact frequency stability. But the fast ones like synchronizing inertia, so which is synchronizing power and inertia or fast frequency control, also have an impact on the stable power transmission. And the reactive power-based services, they have a large impact on rotor angle stability. And this is something that mustn't be forgotten. Yeah? If we have a strong dynamic voltage support, also the oscillatory, we have less oscillatory stability problems, and we also have less transient stability problems. And of course, voltage support is needed to maintain voltage stability.
Markus, ich bin hier noch mal kurz rein, 5 Minuten noch verbleiben.
Yeah, but that's enough.
Aber ich glaube, du bist on track.
Yeah, I think it's not too bad, yeah. Today, normally, I'm very bad keeping on the time, but yeah. All right. So first of all, let's have a look now on at the technologies that can provide these services. First of all, of course, the synchronous machine power plant, conventional power plant. Conventional power plant can essentially provide more or less everything, maybe except from fast frequency control. Frequency control in a conventional power plant is linked to the turbine. If we say it has a thermal power plant, then we have corresponding ramp rates and so on. And frequency control is normally not that fast, so it's in the time frame of between 10 and 30 seconds, I would say. So the real fast frequency control that, for instance, a battery energy storage system can provide, that supports frequency by active power within 1, 2, 3 seconds, that's then maybe not possible. But we get from these large synchronous machine power plants everything that the system needs, or we can also say the system has been built in a way that it works with the services that a synchronous machine power plant delivers. If we now see less and less synchronous machine power plants on the system, then basically we need other technologies that provide these services. And in the report, we basically discuss which of these services can be delivered. The combination of synchronizing power or synchronizing torque and inertia in this presentation. It is possible also to provide dynamic voltage support with a grid following converter. Not many of them do it nowadays because it's not required by the grid codes and by most connection conditions. I mean, we have wind turbines which generally operate with dynamic voltage control, but it's not a requirement, and therefore the large majority of converter-driven power plants doesn't provide dynamic voltage support. But it's possible without a lot of additional effort. And I've just seen that the new German connection conditions, which are now in consultation, foresee dynamic voltage support as a mandatory requirement for all wind farms, PV farms, battery energy storage systems. In order to be able to provide synchronizing inertia, we either need a synchronous generator or we need a power plant with a grid forming converter. Here you see the red arrow. But if we provide synchronizing power to the system, we always need an active power source that is able to support it. So a PV inverter, for instance, does not have any active power storage capability built in. So if, of course, you can apply a grid forming controller to its inverter, but it must always be supported by some sort of active power, at least in the short term. So what is needed is always either some sort of short-term storage. In case of a synchronous machine, this is the energy that is stored in the rotating masses, or we have to curtail the power plant, which is very costly and typically not an option. So we always have to discuss grid forming converter requirements on a power plant basis and not on basis of just a converter control. It's very easy to add a grid forming controller to any kind of inverter, but this is not enough. What is needed is that it is supported by active power. So we always have to analyze the impact on the complete power plant, on the complete generator, turbine, drivetrain, everything. Yeah, I think this is very important. So let's come to the summary. What is needed to ensure system stability in future? I think what is needed is that the required system services are provided. Needs to be ensured that they will be provided either by variable renewable energies directly or by additional components. So basically the task is to find the most economic combination of these technologies to provide the required system services. In my opinion, of course, we could, or in my opinion, it's not enough just to say everybody should do everything. Everybody must be grid forming if it's not needed. So we really have to analyze what is the need for each of these services and what is the most economic combination of technologies which are then able to deliver these services. And this can, of course, be left up to a market to decide what is the most economic approach, or if TSOs do not want to trust any markets, then I would say then it's up to the system operators or the regulators or the policymakers to assess what an efficient solution to this problem would be. And then there are, of course, other things that are needed to secure system stabilities. I mean, especially because our systems are nowadays generally operated closer to their stability limits. We have to adapt the operational procedures. We have to use more sophisticated tools for operational planning and real-time operations in order to identify in data scales, real-time scales, what the stability limits are. And this can be supported by tools like DSA, Dynamic Security Assessment, or wide area monitoring systems, which are tools which are already rolled out by the European system operators. All right, so that's my summary. I hope it was not too bad time-wise, Alex.
Thanks a lot, Markus.
Good.
It was perfect. I think it's time well spent. And exactly this is what we hoped to have in the webinar, to have this explanation of the very technical questions from a real expert to inform the wider audience. And yeah, we're thankful for the detailed discussions we had before and during the project.
Okay, thank you.
And with that, I will move on to the key findings we have derived from the work in the last year. I will share with you the headlines, and honestly, I will read out the more detailed key findings that we have derived. They're a little bulky, so I suggest you may want to look at our websites once it's available. So first of all, a successful transition to climate-neutral power generation requires a new approach to system stability. System operation methods have traditionally been built around the physical properties of conventional power plants. Wind and solar power and batteries are inverter-based technologies connected by power electronics without intrinsic mechanical inertia. Aligning system stability management with renewables-based power systems should therefore feature high on the agenda of policymakers and regulators. Second, to make informed decisions for a renewables-powered grid, it is important to clearly quantify system stability needs using transparent methods. As renewable energy share increases, grid operators and regulators should carefully evaluate whether there are enough stability resources. Overestimating these needs can cause extra costs and delays in integrating more renewable energy, while underestimating could also threaten grid stability. 3, an optimal approach to system stability should focus on using the most cost-effective resources at the relevant location. For example, while batteries, hydrogen, and gas turbines can provide system services with few adjustments, it can be more technically complex for wind and solar, potentially leading to higher costs and delays. Such considerations should determine whether system operators install new technology or run system services auctions, or whether public authorities set technical provisions in tenders or enforce requirements through national and European network codes. And 4, and last, comprehensive dialogue among system operators, manufacturers of generation and storage, and relevant authorities is critical to identify the best solutions. A shared understanding of terminology is essential to accurately identify system stability needs. The ongoing European Network Code revision is an important opportunity for such alignment, and converging towards harmonized EU-wide standards would further help make supply chains for clean technologies more efficient and thus support the transition to a climate-neutral power system. So I will try to summarize these 4 points, which I suggest you read again yourself. So first, yeah, with the energy transition moving on, we need a new approach to system stability. Second, we need to clearly quantify the system needs. And based on this assessment, we need to identify the most cost-efficient technologies and approaches to get them connected. And finally, fourth, we need a dialogue among the system operators, manufacturers, and authorities to identify the best solutions on national and EU level. So yeah, I'm curious what people think about these key findings. And also, if you had questions to Mr. Poeller's presentation, please put them in the chat. And yeah, key findings and the report will be published later on our website. And I think we can now come to our panel discussion with a short delay. And yeah, so I would like to open the panel discussion and welcome one by one. First, Shurok Balok. She's an operability product manager at the National Energy System Operator of the UK. Welcome. Controls at Fluence, a company offering energy storage products and services, and also active in the European Storage Association, EASE, also active with the network code RFG discussions. Hi, Benjamin. Then we have Annette Janssen. She's Manager Policy and Public Affairs at Eugene, the European Engine Power Plants Association, and also closely linked to EU turbines. Hello. We have Johannes von Schkapp. He's Head of System Integrity in the Energy System Planning Unit of TenneT Germany, a system operator in Germany. And Inga Skrupal. She's a Technical Requirement Manager and Lead Specialist for Grids at Vestas, a known wind turbine manufacturer, also active in Wind Europe. And we also have Markus Poeller on the panel, whom you have already seen. Great. Somehow I can't see all of you at the same time, but should be okay. So welcome all of you and thanks for your time. Yeah, to kick off the panel discussion, I'd like to ask each of you about your perspectives on first identifying system needs and the future evolution of system needs. And secondly, on the most relevant technologies providing system service in the future. What's your view on those two elements? I'd like to start with the system operators to get this system needs perspective and then invite the others to come in.
Sorry for interrupting you, Alexander. Johannes has just left and now he's back again because he had some problems with the audio. You couldn't see him, so there he is. I'm logging off again.
Perfect. Yeah, I think Johannes, you're aware of the questions in case you just missed that. Let's start with Shurok. Could you share your views on these two questions, please?
Yeah, I think just to summarize the question, you were asking us about the how we identify system needs for different services and how do we see these services evolving as well. I think from system operators' perspective, it's important to note that system services would be determined across different time horizons. So there will be services determined near to operation timeframes, and there will be need for services in long term for investment planning and having new assets on the system. So fundamentally, two different views of services as well. Some services, for example, in an RGB system, services like frequency response services, frequent response and reserve as well to manage active power imbalance in real time. A lot of these services will be real operationally close to real time determined and will be relying on existing assets and parties available in the balancing mechanism to help with those services. But in the long term, we also, as system operators, will be looking at 10 years out or 5 to 10 years out to understand how our system looks like in terms of expected energy landscape and try to understand if the system stays stable. So there will be need for new services like having new assets to provide voltage management, for example, or new assets to provide system stability, either locationally or on a national level. So yeah, it depends on timeframes and then different assumptions on the layouts of what the energy landscape looks like. But as Marcus was saying, I think, and Marcus' report is going to mention that as well, that there's need for more power system analysis, especially dynamic analysis of the network, not just for the real-time operation system, but also future systems. I think this is where operators have to do more in terms of doing more analysis going forwards to understand what system needs are. I'll just pass on to Johannes for his views.
Thanks, Sherlock. Perfect. Indeed, Johannes, you want to come in?
Yeah, thanks also for the chance to speak here. Maybe first of all, also would like to express my satisfaction that the topic of system stability now comes where it belongs, really in the focus of what you just said, policymaker, regulators, the public, because in our point of view, this is one of the most crucial success factors in both, and at the same time also challenging success factors to facilitate the energy transition. And this is why it's really a good thing that Agora is also focusing on it, and we are happy to contribute also our view. And in addition to what we just heard, we are really having this changing energy system from this synchronous machine driven system to an inverter-based system, where we are also learning how the system behaves. So what we just heard from Mr. Poeller with regard to voltage frequency, angel stability, we are having well-developed determination assessment methodologies. And for the controllers, the resonance stability, we also are gaining experience, but this needs to be developed more. And this is also being done also together with our other colleagues from the other three TSOs in Germany. So this is a very complex and big topic to determine those. And on the second question, I think you also asked about the scarcity we are already seeing. So in our point of view, the transition phase we are currently in from deciding on a CO2 neutral, carbon neutral energy system to where we are aiming for in the target year of 2045, this transition years are very crucial in our point of view. And we are currently already having high utilization of the grids. We are having regions where power plants, big power plants are switched off. And this already forces us to some also unconventional measures. And one is, for example, when looking at our big DC connections onshore, we are not waiting for commissioning of Südlink and Südostlink. We are setting the converters in the south into a STATCO modus.
No, you were muted for a second.
So this is where we are seeing scarcity and how we see them.
Thanks a lot for the contribution. I would then hand the mic over to Benjamin. Afterwards, Annette and Inga.
Yeah, thank you very much.
Benjamin, you want to come on from the technologies and battery perspective?
For us on the manufacturer side of converter fed battery energy storage systems, it's not so much about where in the system the needs are for more synchronizing power or fault current, because that's something that already comes defined. Our customers, project developers come to us already with goals for their business case in mind. On our side, it's much more about the time at which certain services should be provided and certain services should not be provided. So we have some island projects, for example, where when they have high renewables, our battery system operates as grid forming. You have the synchronizing inertia, you have fault current, you have a very fast reaction to support frequency and voltage. But this island also has times when they have no renewables and they have tons of traditional spinning steel on their grid. And then there's no reason to sweat the battery, let's say, so we can transition back to grid following. And these types of controls we see as we move forward, also in the larger European grid or in other grids, you will not always need all of the services everywhere. And so to have the flexibility on your controls to be able to transition between grid following and grid forming, or to, let's say, crank up the grid forming in terms of your inertia time constant, if there's a particular day where you need more inertia, that's something that we're looking at and we have developed already for projects. And of course, then just region to region, what are the different kind of flavors of grid forming, the rock-off curve that NISO provides for their inertia, their Stability Pathfinder service tender, that looks different than what we're seeing eventually coming out of ENTSO-E and other grids. So even if we have a common definition of grid forming, it still seems that regional pockets will have slight variations of their own. I'll hand the mic over.
Thanks, Benjamin. Over to Annette.
Yes, morning, everyone. Yeah, thanks for the invite again. Happy to be here. Maybe before I answer your questions, I'm very happy you're putting this in the spotlight, this topic of system stability, because indeed it is a huge challenge. And I think the first step towards solving a challenge is recognizing it is there. So yeah, congrats for the webinar and for the report as well. More to the question on, what is my perspective of system needs? I mean, system needs, the needs are essential for manufacturers. We need to know what the market will want. And then the manufacturers, who basically their job is to provide solutions, can start working from there. So yeah, that's I think something we all agree on. Of course, then we could discuss on how to identify the needs and so on. But yeah, knowing the needs is really the first step. When it comes to relevant technologies, I mean, I would maybe flip around also a bit your conclusions or the findings, where you say, well, the issue is, what will be the impact of high shares of inverter-based, so of variable, let's say, resources on the system. Well, this is not the issue. The issue is not that we have renewables, because this is what everyone wants, right? The issue is that the spinning masses, the classical power plants, and that's what I represent, so we don't really know what we're going to do with them. So we know that, we have half of the capacity today in the power system in Europe is still spinning masses, more or less. It's really rough numbers, but let's say half of it. So we want to kind of phase out coal. That's a given. We want to phase out gas. Okay, but then what do we do? And so my message here is to say, well, considering the size of the challenge, we need to find and look at all available solutions. So it will not be either or. It will be really, let's check first what there is, and then how we can have worked them best. And I think this was already said by some other panelists before. So yeah, I can go into further details later.
Thank you.
Thanks.
Perfect. And finally, Inga.
That's probably the disadvantage in speaking last. I can only underline what already have been said. I think it's really important that we have that exchange here, and that we're talking to each other. Also, when it comes to identifying system needs, there we heavily rely on the grid operators to provide us that input and to build the knowledge for us to provide also, or to provide back information or knowledge base for them, and what kind of solutions could be commonplace and could be developed. And when it comes to the most relevant technologies for solving those problems and those system needs, that also can only be then derived out of, for example, the report that you made, but also communication exchange and in cooperation. I think that is the most crucial part going forward.
Maybe before we go into the second round, a short follow-up. Like Mr. Poeller before said, maybe not all technologies need to do everything. So could you give a bit of more insight on you're saying, okay, wind turbines can provide system services. It needs to be defined. But could you give some more insights in this arbitrage between having grid following connections and then have a standard turbine that can be connected easily versus a more complex grid forming inverter connected turbine that needs to fulfill more services and then which is more difficult maybe to design. Could you shed a light on this, on the this arbitrage?
When it comes to wind turbines, that is the main change when you have then a converter-based generation is that when you go from grid following to grid forming, that you basically strengthen the connection between the grid and the electrical side towards the mechanical parts. So the main advantage we had while we moved like 15, 20 years away from synchronous connected wind turbines to converter-based wind turbines is because we could decouple the mechanical parts from the electrical grid. Now when the converter is switching to grid forming, this connection is again strengthened. That means it has impact on mechanical parts of the turbines, like all the things that are impacted by load and already also by wind, rotor blades, drivetrain, tower, and then also foundation. So that makes it rather complicated to also then evaluate what needs to be done to compensate for those additional loads to not negatively impact the lifetime of the wind turbines and to keep the risk low related to grid forming. So there are some constraints and some risks that come with it. And different measures that can be taken, for example, adding additional battery storage to a turbine, then which then significantly could increase costs then. That is something that needs to be discussed. What are then the inherent capabilities? How it is, for example, requested in the RFG in the current draft, that it should be within inherent capabilities. But to evaluate what is then actually the outcome that can be provided inherently, that is also difficult to say without the lifelong experience and all the possible interaction that could then occur if a lot of plants are doing grid forming.
Thanks for these deeper insights. Let's go into the second round. And I'd like to talk now about strategies to ensure sufficient system services are there. So what is your view on in how far or under which conditions it could be better that TSOs are investing in grid equipment? In how far or where would tenders for system services be the best choice, or where general connection requirements, either on national or on EU level, would be the best choice? Do you have a view on the best choices, or how to get there? Do you have a few or experiences in taking part in auctions for system services, or organizing those auctions? And here I'd like to start with Benjamin. I think you have some experience here, then followed by Shirok and Johannes, and then the other two.
Sure. Thanks very much, Alex. So generally, we have from different regions or different countries already some, I'll say, new services that start to address some of the issues that Mark has lined out in his slides. You have in Ireland the fast frequency service, which is indeed very fast when you compare it to what we have still on the mainland of Europe. NISO did something similar a few years ago with the dynamic containment, or even before that, enhanced frequency response. And what I want to underline with all of that is we've already seen this kind of general trend of services getting faster and faster and more dynamic. We went from week-long bids in Germany for primary reserve power to now getting down in the UK, we're down to the half hour. So again, coming back to the controls and system controls, being able to change your operation at the drop of a hat based on the broader system needs is something that we continue to see. What we haven't yet seen is that this faster frequency response, that is something that wind turbines and PV have offered, at least in one direction in different markets. But rather than starting to look at that in the NSOE regions and in the main synchronized area of NSOE, we're jumping straight now with the new RFG to grid forming. So it seems like there could still be a trade-off there. Batteries, of course, are very well suited for grid forming. We also have physical limits, and the batteries business case is changing. We used to be doing only those frequency response services. And so we always had, let's say, a state of charge somewhere around 50%. So we could serve both up and down. But more and more and more, these batteries are being used for energy arbitrage. We have negative prices and we have high peak prices. And so more and more and more, these batteries are sitting fully charged or fully discharged. So you also have to think about not just the context of some stability system services, but how do I provide that in parallel or on top of other market services? Because without those paying the bills, no one will build the battery in the first place. So I think that's in terms of strategy, that's something that we always have to keep in mind. And I would be happy to then hand it over to anyone else.
Yeah. Shirok, you had a program in the UK over the last years. You want to give some insights on that and your first experience on system service auctions?
Yeah, definitely. Before I do that, I think maybe pick up on Benjamin's point around the services being provided, different services being provided in parallel. So that is something we would be calling stacking of services in our markets. And I think, obviously, from Benjamin's perspective, there'll be different challenges for manufacturers and developers to ensure that they can do all of the services, and that's where the revenue is coming from. But from system operators' perspective also, I think there are challenges around ensuring that each asset that's providing all these services in parallel can actually provide the services in parallel, and also ensuring the services are provided, because at the end of the day, it's the cost to the consumers being able to provide the services as well. So from operators' perspective, there are different challenges and things we still need to work through in understanding how do we ensure that all of the services are guaranteed and provided, which we have contracted for as well. Alongside that, the services, some of the things Benjamin also mentioned, the dynamic containment service, like fast frequency response service, we have been trialing over the last few years as well. All of those services are close to operation timeframes, but what we have done differently over the last few years, we have been running pathfinders, which have been a new thing for us, and we have been doing it by calling it learning by doing approach, because it's an experiment for us in the beginning, and then we've tried to adapt and come with something more permanent as well. But the significant difference with those tenders we have been running are that we have been awarding long-term contracts to commercial providers, so up to 10 years worth of contract for somebody, which is something we haven't done in the past, which has triggered new investments. So there are benefits of running those tenders. We have seen benefits of getting long-term prices locked in that context. So we have run voltage pathfinders, which we procured, in which we procured high voltage or a reactive absorption capability, because we were seeing high voltages on our system in certain areas. So we through the tendering process, we triggered some new investment, new assets to be built. We have also run stability pathfinders, where we primarily looked for national inertia and locational short circuit level kind of service, but short circuit level was a proxy to system stability measurement, but it's always tricky to define what that metric is. So there's still a lot of work that needs to be done to understand what is the right metric for system strength going forward as well. But that's what we procured into those contracts, which triggered us to have new synchronous compensators being awarded contracts in areas of the country. And some of the progress on those projects is, one of the projects is energized this week. There'll be more coming over the next few months as well. But as a result of that, we contracted 5 grid forming batteries in Scotland. I think that's the biggest, biggest project, because that's the first time we will have a grid forming battery in our system, which would have undergone our grid code compliance. It would have undergone testing as well. So in terms, it's a big milestone for us to have those contracts in place. But with the advantage of the long-term tenders has been that the assets can lock in long-term pricing with us, and hence they have more cases to build. But we also then see benefit to the consumer cost by having an asset that is there to provide a long-term service to us as well. Lots of learnings as well through that process. Lots of things we have changed from the first tender, which we ran back in 2020 or 2019. Going from there, a lot of things have changed. On the GB system, our biggest challenge has been connections as well. So we have adapted the process to ensure that we change how we tender these things in terms of connection as well, and sort of also understanding how we leverage existing connections for new services. So we have been developing midterm markets as well for voltage and stability to allow us to have locked in contracts for a 12-month period, but 3 years out. So sort of bridge the gap between long-term and short-term, because we will always need something in real time, but it's trying to make sure that we always have some sort of leverage in between the operations and long-term investment time frame as well. Yeah, a lot to talk about. There's a lot on our website, so I'm sure people can find more information there. But
yeah, I wish we had more time reserved for the discussion, but unfortunately we don't. So time is running. On this point, maybe very briefly, Johannes, then Inge and Annette, and then we do a very quick last round. Yeah, Johannes.
Okay, I'll try to be quick. Just maybe to give a perspective how we are doing it in Germany. We are seeing the goals, the scenarios we want to achieve in order to get the carbon-free energy system in 45, and therefore we are determining the system needs. What we just saw on regarding stability. And there, as you nicely described, Alex, in the beginning, we have 3 pillars doing so. So the very short term, we try to do in our own grid, like also we just heard, yeah, with TSO owned assets. The second pillar is then at some kind of market, which we really see as a big step towards providing those system services. And of course, we have the grid code available. And the second and the third one, they kind of interact or are dependent, because we will get grid requirements anyhow through grid codes, and ultimately they can also be used then for future markets we anticipate. And just to bring a number in, having all conventional power plants shut off and having this in renewable energy generation, we are seeing the demand of 1,500 gigawatt seconds of inertia demand. And this is so huge that we really need every grid connectee, every asset connected to our grid contributing to this. This means batteries, this means also new power plants, gas, hydrogen power plants, but also the big potential we see in the North Sea with also the wind turbines. So this is really a challenge we are having, and the demands are so huge that we really need to tackle these together. Yeah.
Markus, you raised your hand. You're muted. You're still muted.
No, I can talk. You can in the end. It's fine. Yeah, we can first of all.
Yeah. Then Inge first, and then Annette. If you want to come in. Yeah.
Yeah, I think when we are talking inertia, I think it's also important to look at the socioeconomic costs, especially, of course, I'm from a wind turbine manufacturer. Then I'm always thinking about all the additional loads that would be brought to the mechanical parts. And that would mean that we would need to provide that additional inertia. We would need to install batteries, and those batteries to also transfer that power to the system would also need their own converters on top. And that would increase also, for example, the size of the nacelle significantly. And when we're talking then at every turbine would need to have that also offshore, or we would need to have a huge battery system centrally installed on the plant offshore. That would increase the cost significantly for those offshore projects. And there needs to be some kind of a remuneration in place to make that worthwhile, to also for developers to invest, to continuously invest in those projects then. And I think it's when we're talking about grid farming, and if we're differentiating at the moment in the RFG, in the draft is written that everything that is provided or must be provided within the inherent capabilities, then this is limited. It doesn't enforce design changes to turbines or to PV or battery storage or so. But when we're talking about type C and type D, currently in the draft, the grid operators can require extra synthetic inertia. But that comes to different costs for different technologies. So I think we also should have a focus, or should be all interest in making sure that the end consumers' costs stay as low as possible, to also increase the acceptance of the energy transition. And therefore we also need to embrace the differences of the technologies and the different options that we have. And we have a lot of options to address the inertia issues, to also keep those costs low. And I think we need to have an open discussion about what's the most efficient way to do that.
Thank you. And I think we really need to speed up. So Annette, and then maybe prepare your 2 words or maximum 1 sentence for the last round. Annette.
Yes, maybe, yeah, we heard a lot of, about the challenges. And as I said, it's good to be aware of these challenges because they're huge. But what I wanted to get back a bit to the first question and say also that there's a solution, which is the existing assets. As Shurok said, we need also to build on that. So today we have around 200 gigawatt of gas plants in Europe. And there it's really important, I think, and this is not something I really saw in the presentation. It's important to differentiate between capacity and the energy provided. So normally we talk about, well, in the future, let's say, I don't know, 70%, then 90%, then 100% of the energy should be provided by renewables. Well, okay, but does this also mean that 100% of the capacity will be wind and solar? I think this needs to be differentiated. And from the gas power plant manufacturer perspective, there is kind of a relatively easy solution that you can do, is separate the prime mover, which can be an engine and a turbine, from the generator. And then you can still provide, let's say, especially, let's say, inertia. So just as awareness, because that's a solution that is there, and it needs to be it can be implemented relatively easily. Now to the how to kind of ensure that let's say the system, or that the technologies will be there. Well, you talk about grid codes, and then about markets, or there's also bilateral contracts. I would say, all these things are not the same. So grid codes are kind of an essential technical requirement, right? It's what you need to comply with if you want to connect to the grid, and you will not, to ensure that you will not put the grid in danger of collapsing when you connect. And I think this you need to have in mind, or everyone needs to have in mind. It's maybe not something to then procure services, right? It's 2 different things. So I'd say grid codes are really the essential technical requirement, and it's not a political kind of wish. It's something you need to comply with. But then if you want to build up a market, and you really see that there's a big need, from our perspective, and I think in general, we would say it's always, if you want to find out the price and want to find out what there is, well, try to organize a market, try to see what there is. And I think there the UK experience is a good one. Then, of course, if there's a little need, our plants that provide Black Start, but Black Start is not something that normally is needed. I mean, everyone hopes it will not be needed. And there are not many capacities needed, many plants needed. So there you have bilateral contracts, and that's something that is already existing. So yeah, I would say, yeah, there needs to be a hierarchy, let's say, of things here. It's not everything at the same time. It's like, let's start with the grid requirements. That's an essential part. But then given the needs, we need to go also into other, mechanisms. Thanks.
Thank you. Markus.
Yes, I mean, that's exactly what I also wanted to add. As I have mentioned in my presentation, the main impact of variable renewables comes from their passivity. So it's not that they would do things that really disturb the grid in terms of stability, but there are maybe some things which they don't do. And the main stability impact comes from the disconnection of rotating power plants, of synchronous machine power plants, and not so much from the addition of variable renewables. So of course, when we have a high penetration scenario, then the conventional power plants will at least be temporarily disconnected during times that they are not dispatched when there's high wind and PV generation. But I also think that, first of all, we should use the potential that there is, and we should simply try to enable the conventional power plants of remaining synchronized during times that they are not generating. And what is needed are these self-synchronizing clutches that you can install in the drivetrain. I mean, for an existing power plant, it's actually quite costly to upgrade them because you have changed quite a lot. But for new installations, this can be added at relatively low cost. And here in Germany, I mean, for instance, there are plans for many new H2-ready gas turbines. And I think a first measure could be to equip them with these self-synchronizing clutches, and then a lot of inertia, but not only inertia, we then also have their contribution to dynamic voltage control, reactive power, short circuit power. Everything would be there, and this typically at exactly the same locations where the big coal-fired power stations are generating nowadays. So I think we should really start from the low-hanging fruits, yeah, with the least costly solutions, and then move forward towards the expensive solutions. And another remark in terms of the requirement, Johannes has just dropped the number about the inertia requirement. I mean, there are different numbers around about what is required. Some numbers come from the context of the German stability studies. We also have seen numbers that have been calculated at NSOE level by the corresponding expert group. And these numbers are highly different. And I would say that's another thing which, in my opinion, is very important, that we really clearly identify the need for especially inertia. I think it shouldn't be over conservative. It should, of course, be conservative, but it shouldn't be over conservative. And the numbers should at least not be different by an order of magnitude. Yeah, then it's not credible. So we really should come to a methodology and to constraints to the system that allows us to really agree on a number at European level and also at national level.
Okay, we have planned a third round, and I would like to give you the chance to have a last word or two last words, maximum a sentence. We overall have 1 minute left. Inga, Annette, Benjamin, Johannes, Schrock. Is there a last message you want to give? You can also pass on to your colleague.
I'll try real short. I saw also a Q&A, someone asking about, is there a standardized definition? Now, still not, but it's coming. Senelec has been doing some great work. FNN, VDE, FNN, the NSOE expert working group on grid forming controls. We're getting there. It's coming out soon. And part of that is we're not necessarily saying everyone has to do grid forming or everyone has to do this much of grid forming, but how do you define it? How do you test it? and how do you quantify it? So we've heard many times about making sure that the costs are fair, that we're not over-dimensioning, that we're respecting different technologies, and all technologies have limits. Even with the synchronizing clutch, there's going to be losses in that system. So someone has to pay for the losses. How do we remunerate that? And I think having Europe-wide harmonious standard for testing would be great. Thanks.
Inga, one sentence.
Everything that is a system service, like inertia provision, should be remunerated and to keep the socioeconomic costs low. So it should be on a market-based approach that enables all technologies to chip in and place their bid or to get their piece of the cake.
Thank you. Annette?
Yes, I can only underline what Inga just said. So system services, if a service is provided, it would need to be rewarded. If not, it will not be provided and the investment will not be made. I think that's the essential thing. Maybe on the grid code, because I would have two messages. One is set technically doable requirements. It was said by others, but I think it's really essential. Don't try to kind of aim for the moon with something that is not done for that. And the second is like make them as clear as possible. We still have different interpretations today, and this could be kind of maybe improved, and maybe start with making it as clear as possible, and then we see for the rest. Yeah, thanks.
Johannes.
I like the quote being done before. This is very short. Stability becomes different. I like that. And it's, as we saw today, a joint challenge. So let's get it started.
Thanks. And finally, Shirok.
I think just to echo with everybody's thoughts here, but from a Great British perspective, I think our system is evolving towards renewables a lot faster than a lot of other countries. So we are seeing a lot of challenges where we have to do some things without having some precedence of it. So yeah, there's a lot of learning from us, definitely, that maybe there's a lot of others that can take from us, but there's a lot of stuff we have to do ourselves because nobody else has done it. So a lot of challenge for us to navigate what different things mean for us. But it's been, the stability is a hot topic, and I think it's a very important topic that needs to be discovered further through a lot of collaboration and working. But that's all from me.
Thank you so much. I close the panel and quickly hand over to Emmeline. So I'd like to thank you so much for your time. It had sparked a lot of questions to me, so I could ask you for another hour, I guess. I hope it also sparked questions in the participants, and please feel free to reach out to your contacts and to us if you have those questions. We'll try to answer the questions that were sent in the chat in written. We unfortunately don't have the time for that. Also, the Menti will be shared with you later on as in respect of time. I'm sorry. Yeah, thanks to Mr. Poeller. Thanks to the colleagues in the background organizing the webinar and making the smooth functioning possible. And with that, I hand back to Emmeline for the final wrap-up.
Thank you very much, Alex. And indeed, thank you to Mr. Poeller and our panelists. I think you collectively did a great job at shedding light on the trade-offs that we have with this issue, which is that on the one hand, things are going very fast, and we're asking that this transition be very fast of power systems. And so there's really this question, what decisions do we need to take now so that at some point we are not obliged to slow down things because we run into system stability questions. And at the same time, we have this very clear requirement that we need to keep this transition cost efficient. I mean, that one of the flagship initiatives of the European Commission in the first 100 days, aside the Clean Industrial Deal, is going to be this affordable energy prices action plan. So this is really what's at the core of this question. What's also the trade-off that is at the core of the finalization of the grid code. I'm not sure we had European Commission in the room today. I think they had conflicting requirements, but they did participate in some of our previous stakeholders workshop. I do hope that this work and those discussions can help informing their work on this. And my last point is we definitely need to keep the conversation going. This conversation needs to keep going. We hear different assessments. We hear that we need common definitions. I guess at some point we need common standards as well for manufacturing so that we have efficient supply chains. I hear that we need common methodologies or common understanding on how you do the quantitative assessments of these needs. And I also hear that, or you know, infer from what was said that we might need more information or more information sharing on what does it cost for different types of assets to provide the services. So we need to keep this conversation going, and it's very important that we have platforms at EU level, or more than EU, because the UK is showing us the way here. And you know, maybe that's something we need to extend this dialogue to beyond Europe as well. We have participants from many countries today. And on our side at Agora, we're happy to think of, you know, how we can leverage on our INET network of think tanks to facilitate that. With this, I will end our webinar. Thank you very much